everyone. From now onwards we shall discuss some problems related to what we have studied till now. So let us start with the first problem of Brownian particle in harmonic potential. Till now what we have seen that the Brownian particle is only bombarded due to the small tiny fluid molecules, okay, but there is no external potential. So earlier the equation of motion for the Brownian particle was dv by dt is equals to a drag and a noise term due to the bombardment and drag due to the movement in the fluid, okay. But now there is an, let's say, a harmonic potential present, then particle will feel an extra force which is proportional to, let's say we are considering only one direction, fx minus del u by del x, where u is the, u can be any external potential, but for our case we are considering u as a harmonic oscillator or harmonic potential. For that case, let us choose 1 by 2 kx square, where k is the spring constant and then fx will be minus kx. So there will be an extra term, this force term will be added, so minus kx. Now we want to see that how what will be the form of the mean square displacement and the velocity correlation, what is the form of the fluctuation dissipation theorem, let's say, etc. So for that we need to first solve this equation. So let us write everything in terms of x m d2x, so x is a function of time, dt2 minus m gamma dx by dt minus kx plus eta t. Eta is our old random noise which we had seen earlier also. So I forget to mention one thing, that this kind of equations are known as the Langevin equation. Langevin equation. Okay. So let us start. Now there are two time scale in the problem. One time scale is the Brownian time scale, tau b is equals to gamma minus 1. Other is due to this, so first is coming from this term, the drag term, and other is due to this potential. Okay, yeah, so let's just define this other time scale as tau k, let's say tau k, which is kappa over gamma m. So this is kappa or let's say k. So now to just to have an idea that what is the order of this time scale, so this gamma from this m gamma is actually coming from the fluid viscosity, so 6 pi eta av. And if we assume that a particle size is micron size, 10 to the power minus 6 meter, and let's say the fluid density is of the order of 10 to the power 10 to the power 3 kg per meter cube for water, let's say, and so the mass of the particle will be of the order of 10 to the power 3 into a cube, so 10 to the power minus 18, so roughly 10 to the power minus 15 kg. Then if you calculate, if you solve this, so eta is of the order of 10 to the power minus 3 kg per meter. If you solve, gamma will come out to be of the order of 10 to the power minus 7. Gamma inverse will be 10 to the power minus 7 seconds. So your time scale tau b is of the order of 10 to the power minus 7 seconds. And in general, for biological systems or for this harmonic, these kind of potential are actually applied to track the particles. There is a name in soft matter called optical tweezers. Which is used to guide the particle through the way we want, through the potential, to confine the potential, to confine the particle, etc. So these are of the order of 10 to the power minus 3 seconds. So for all practical purposes, we can assume that this tau b is very less than tau h. So we can safely ignore this inertia term. So if you ignore this inertia term, your equation will look like this: dx over dt is equals to minus kappa over m gamma x plus eta over m gamma t. So by ignoring that inertia term, we have only now one time scale, which is kappa over m gamma in our problem. And this is actually easier to solve. So now let us start solve it. So similarly, the integrating factor will be dx over dt e to the power minus kappa over m gamma plus kappa over m gamma x e to the power kappa, oh this is plus actually, not minus, kappa over m gamma t is equals to eta over m gamma, let us denote it by t prime. M gamma eta t prime e to the power kappa over m gamma t prime. We can, since we have to integrate it, so we will integrate it up to 0 to t. That's why I just changed the variable from t to t prime for now. And this thing is d by dt of e to the power kappa over m gamma, or k over m gamma t prime x t prime x, just write x, okay, and eta t prime m gamma to the power kappa over m gamma t prime. So x will be, so let us integrate it then from 0 to t. So this will become xt minus x naught, okay, so xt e to the power kappa over m gamma t minus x0 is equals to this integration eta t prime m gamma e to the power kappa over m gamma t prime dt prime. So this section is the detailed tutorial kind of thing, or detailed problem solving session. So I will solve each and every step for your clarification. So xt will be x0 e to the power minus kappa over m gamma t plus 0 to t eta t prime over m gamma, we can push this inside, and e to the power minus kappa over m gamma t minus d prime dt prime. So this is the equation of for the expression for the xt. Now one can take the average over the all realization of the noise as we have done earlier. So if you average it, then nothing to average here, so x0 e to the power minus kappa over m gamma t plus this term will be vanished because the average, okay, eta t prime is 0 and the second average is t, or the correlation t prime is gamma delta t minus t prime. So this is, and if you now take the so just now what we want the x square. So x square will be, so if you just take the average again, then you will have over the initial conditions, then you will have x0 average e to the power minus kappa over m gamma t. Again this will be 0 because, and one more thing is that we are considering that the whole thing is again in equilibrium, thermal equilibrium. So okay, so let me do the next step, then I will explain. So x square t will be x0 square to the power minus 2 kappa over m gamma t plus the linear term when we shall average it over the all realization will vanish. So this is the linear term, linear in eta t plus the square term in eta. So 0 to t dt1 eta t1 m gamma square okay, this way 0 to t dt2 eta t1 eta t2 over m gamma square e to the power, so kappa over m gamma t1 plus t2, and let me pull this out of the integration. So there is a linear term e to the power minus 2 kappa over m gamma t. Now let us do the average over all realization. This will be 0, linear in eta t, and from this we will have again x0 square e to the power minus 2 kappa over m gamma t plus e to the power minus 2 kappa over m gamma t, and if this is delta correlated, so gamma over m small gamma square, and we shall have integration. So if you do the integration, this will come out, so m gamma over kappa 2 kappa actually, because when you substitute t1 is equals to t2, this term will be 2 kappa. Okay, so 2 kappa and e to the power 2 kappa over m gamma t minus 1. So just put it inside, then it will have x0 e to the power minus 2 kappa over m gamma t plus gamma over m small gamma 2 kappa, okay, 2 kappa m small gamma 1 minus e to the power minus 2 kappa over m gamma t. Okay, so this is the average over all realization. Now if we average over the ensembles, then you will have not ensemble, yeah, you can say ensemble, because we are actually averaging over all initial condition of this x0 average to the power minus 2 kappa over m gamma t plus gamma. Okay, so we can write it more beautifully, minus gamma over 2 kappa m gamma e to the power minus 2 kappa over m gamma t plus gamma over 2 kappa m small gamma. Okay, now the question is, what is this x0 average, or what is this eventually? Should it depend on time? Since we are saying that we are in thermal equilibrium, so this eventually has no time dependence. So for this thing to be vanished, we will have this term 0. So x square 0 average is gamma over 2 kappa m gamma. So this is like a fluctuation distribution theorem, but we don't know this value. So if you know the probability distribution for this x0, you can solve it. Okay, so let us for now assume that this particle follows the Maxwellian distribution or Maxwell-Boltzmann distribution. So this probability of x0 will be proportional to e to the power minus 1 by 2 k x0 square over kbt. And if you took the average, then you will get that x0 square is actually kbt over k. And from equipartition theorem also we can say that, so equipartition theorem says that each quadratic degree of freedom has a, if it is in thermal equilibrium, has energy of half kbt. So x0, so 1 by 2, this has the units of energy. 1 by 2 k0 square will be kbt by 2. So this x0 square is actually kbt over k. And if you substitute back into this, you will have gamma over 2m k, this is equals to kbt over k. And you will again get the same form, 2m kbt gamma or 2m gamma kbt. So this relation you actually seen before in the case of particle which is moving freely into the bath of the molecules or the fluids. Okay, so you see that this form of the fluctuation dissipation doesn't change due to the appearance of the harmonic potential. Okay, now let us look into the what is the mean square displacement. So what will be the displacement? Let us define displacement as xt as x0 minus x0, and naturally the average of xt will be 0, but this mean square x square t mean square will be non-zero, and we are finding it this value here, minus x0 whole square this. So just simple calculations. What is your xt square? Okay, just expand this term again. So this is xt square minus or plus x0 square minus 2xt x0. So we know this term, we have to calculate this xt x0. So xt was x0 e to the power minus kappa over m gamma t plus 0 to t eta t prime over m gamma e to the power minus kappa over m gamma t minus t prime dt prime. So now we have to evaluate this integral xt minus x0, this correlation xt x0. Okay, for that let us start from this, otherwise there can be some other results which you will not be understand. So just start from here as we have done last time. So what was xt? This, and xt prime will be just the prime. So what will be the product? So again we can easily drop the linear in t prime term, and then we will have this x0 square e to the power minus kappa over m gamma t plus t prime and the cross terms plus 0 to t dt1, 0 to t prime dt2, average of eta t1 eta t2 e to the power, okay, there will be two things, 2 kappa over m gamma t minus t1 and e to the power minus 2 not kappa k t prime minus t2. Okay, so and the average. So we will have x square 0 e to the power minus gamma over m t plus t prime, okay, m gamma square. So capital gamma m gamma square e to the power minus 2 kappa over m gamma t plus t prime. And if you solve this integration, so this is, so again we have to choose that whether t is greater than t prime or t prime is greater than t. For now let us assume that t is greater than t prime. So we are integrating over t1 and t2, and both have different limit. Okay, this is t1 is going from 0 to t and t2 is 0 to t prime, but the delta function will ensure that the over which we are integrating, let's say we are integrating over dt2 first, t2, then t1 will only go up to t prime because of this delta function. Okay, so this is delta of, so if you substitute the value of delta, then t prime integration will be gone and this will be replaced by t prime e to the power 2k over m gamma t1 plus t2, and this will be 2 times t1. Yeah, so that's why 2 is coming. So actually there is no 2 here, it's only k. Okay, 2t1. Now if you solve it, you will have x0 square e to the power minus kappa over m gamma t plus t prime, and again plus gamma over m small gamma square e to the power minus 2 kappa over m gamma t plus t prime, and m gamma over 2 kappa, 1 will be out, e to the power 2k t prime minus 1. Okay, if you solve it again, you will have gamma over 2m gamma k and e to the power, so this will be plus, so minus minus 2k over m gamma t minus t prime. Okay, minus 1, so 1 you can take this side and you will have x0 square minus gamma over 2m kappa k and exponential minus kappa over m gamma t plus t prime. But again, from the fluctuation dissipation theorem, this term will be 0, so we will have xt prime as gamma over, okay, yeah, one thing I forgot, that this thing is for t and there will be a 2 also which I missed. Yeah, so we will have gamma for t greater than t prime, and we will have t prime minus t for t less than t prime. So again, as in case of the velocity correlation, we shall have this kappa e to the power minus 2k over m gamma mod t minus t prime. Okay, okay, yeah, there will be no 2 here, there is no 2 here, and there is no 2 here also. Okay, so we will just have kappa. Okay, so your xt correlation with xt0 will be just gamma over 2mk to the power minus k over m gamma t modulus. Okay, so this is the important result. Now we can determine the displacement, mean square displacement. Okay, so our mean square displacement will be now, so this is x squared t will be xt square plus x0 square minus 2 xt x0. Okay, just substitute the values. So the average value of this will be same, right? So it will be 2 x0 square minus 2, this is gamma over 2 m gamma k e to the power minus k over m gamma mod t. And again, from fluctuation distribution theorem, we know that the x0 average square is kbt over gamma k. We substitute it here, 2 x0 square kb, okay, 2 kbt over k minus, and this one is 2, so 2 kbt m gamma over 2 m gamma k e to the power minus m kappa over m gamma t. So we will have 2 kbt over gamma 1 minus e to the power minus kappa over m gamma mod t x squared t. Okay, so this is your mean square displacement. Now you can see that this mean square displacement for time okay, so time dependence we will see later. First let us derive the expression for the velocity correlation as well. Okay, so now what will be the velocity correlation? So velocity correlations, Vt is d by x dot. Okay, so Vt is x dot t. T prime will be x dot t prime. So you can just see that, just evaluate this one. So xt, so this Vt to V0 is nothing but xt dot x0 dot. To say this is a bit wrong actually, because the displacement, we have to take the average dot product of the displacement. So the right thing is this one. So x t so for t prime, this is xt minus x0 xt prime minus x0 a derivative of this. So we can write this way, delta t and delta t prime 2. This you can check, this is easy. Now if you expand it, so you will have delta t, you can just simply write del 2 del t prime of delta of x, delta of xt minus t prime delta of x0 from the first one. This one is also true. Okay, again this will be, this can be written as minus del 2 del t2 over delta of x. Okay, the pen got changed. Delta of x t minus t prime delta of x0. Okay, this you can check, mathematics. And so this will be x dot t x dot t0, then can be written as minus delta 2 delta t2 delta of xi delta of x t delta of x0, and this is equivalent to del 2 t by del t2 xt minus x0 whole square, or the mean displacement square, derivative of that. So we have this mean displacement square value, and if you just do the derivative, so what is this? x0 xt minus x0 whole square average was 2 kbt over gamma 1 minus e to the power minus k over m gamma mod t, right? So if you took the derivative 2 times, you have to write this as a theta function. So e to the power minus mod t over k over m gamma is actually can be written as e to the power t over tau, e to the power t k over m gamma theta function minus t plus plus of the minus t k over m gamma, and for the theta positive. Okay, just for theta t. Okay, so these are the step functions, and you know that the derivative of delta function, derivative of step function is actually a theta function, delta function. So just use this property and you will obtain that Vt V0 is nothing but 2 times kVt over m gamma delta t minus kVt and kappa over m gammas, this to the power minus t over kappa m gamma. Okay, so this is the expression for the velocity correlation. Now let us see the limiting cases. What will be the limiting cases? If we just simplify a bit, so we will see that this is 2d delta t minus, and this is kBt over m gamma, so d and m gamma over kappa to the power minus 30 kappa over m gamma, velocity correlation. And we, for the displacement square, what we have obtained, x square t was kBt 2 kBt over gamma 1 minus e to the power minus kappa over m gamma mod t. Now for very short time t tends to 0, what we shall have? So let us expand it. So x square t mean value would be 2 kBt over gamma 1 minus 1 plus kappa over m gamma t, let's say for t greater than 0. Okay, so what you have, 2 kBt over gamma kappa over m gamma t, and this is nothing but 2, sorry, here we have a kappa. Okay, so this kappa will cancel out, and 2 kBt over m gamma t x square t. This is nothing but the same diffusion relation. So for very short time the particles are actually diffusing. The diffusion process is dominating. Diffusion. And for the velocity correlation also, you can see that this x, Vt V0 is actually for very short time the delta term is dominating. And if you remember, for the case when we have no potential free particle in a Brownian free Brownian particle, then we obtain this relation, 2 kBt over m to the power minus gamma modulus of t minus t prime. So then in the limit tau or tau b tending to 0, because we initially assume that tau b tending to 0 and we neglect the inertial term. For that case, one can write, and tau b is what? Tau b is gamma inverse, right? So kbt over m gamma to the power minus gamma t minus, so you can write this way, t minus t prime over tau b, okay? And the limit tau b tending to 0, this is nothing but the delta function. So what you have? 2 dt. So essentially what is happening, that t minus t prime, for 0 it is delta t. So the limiting case of both the things are actually same. The potential becomes free particle. So if you plot this, what will you have? This kind of things. That initially there is a peak in the delta function, a peak in the velocity correlation. So due to the delta function, okay, and it will decay and then tend to the 0 value, because it is ultimately decaying, so it will go to 0. And if you plot this displacement, mean square displacement, then you will see that initially it has x square is linear in time, but then it saturates, okay? To what? Saturates to this value, kbt over kappa or gamma, k, okay? So we are plotting time lag, velocity correlation, and here also delta t. So you see that how this potential affects the harmonic oscillation. So the fluctuation dissipation doesn't change. Velocity correlation is now has a peak in the time t is equals to 0, very sharp peak, and then it saturates. For free particle it was like exponentially decaying with the time lag. For this it has a sharp increase due to the potential, and then it decreases eventually. And with the x square t, initially it's like diffusion, but then in average mean square value obtain a certain limit, it saturates, okay? So this is actually the confinement, yeah. So for this lecture we shall end here. Next we shall do some more problem on probabilities.